All right, so here we're going to talk a little bit about uh, proofs by induction. Now, one of the reasons that this is important in computer science in the context of proving correctness of algorithms is that there is a pretty decent correspondence between the inductive proof technique and the notion of recursion, or recursive algorithms, recursive programs. Okay? In both cases, in both scenarios, you have a base case. In some sense, you have a general assumption and a general statement. So, sort of three components to how you go about with either of these two techniques. Okay, so it's good for us to have a fairly decent understanding of this. Now, I am assuming that you've seen this in a discrete math class that you've taken previously. Okay, so I'm going to skim the idea here. We will have some homeworks that will help advance this as well. But again, hopefully you're coming into the class with decent background in this area. Okay, so here is the example we're going to work with. This is a sort of very typical canonical example of proofs by induction. And so what we're saying here is we're giving this a name. We're saying this is a proposition in terms of n, okay? And the proposition is basically saying that if I add up all of the integers from 1 to n, right? So what the left-hand side is equivalent to 1 plus 2 plus 3 all the way up to n, right? This is summation notation. We're saying that this is equal to n times n plus 1 over 2. And the claim is that this is true for all values of n greater than or equal to 1. Okay, so that's what we have here. Now, the first thing I want to point out is what we're being asked to prove, especially with this for all n greater than or equal to 1, is we're being asked to prove that the proposition is correct for 1, the proposition is correct for 2, the proposition is correct for 3, and so on, okay, forever, right? So we're being asked to prove an infinite number of propositions. And if you just sort of take a step back and think about it, that seems like an impossible task, right? How can I be asked to do an infinite set of things, okay? But that's where induction and other approaches come in. All right, so let's review the mechanical aspects of the proof. The first thing you would do here is consider the basis, or the basis scenario where n is equal to 1. So we prove that this is true for n equal to 1. So in other words, what we're doing here is proving P1. Okay? And so to do that, I plug n equal to 1 on the left-hand side. So on the left-hand side, all I get is 1. Right? So the left-hand side is the summation from 1 to n. If n is 1, I only have the single term there, and that's a 1. And then the right-hand side, again, I plug 1 in, so I get 1 times 2 divided by 2, which is also 1, and that's the base case. Okay. Then we make the induction hypothesis. Okay. So we assume that Pk is true. Okay. So what's Pk? Well, Pk is what I get when I simply replace n with k, right? So what we're saying on the left-hand side is I have I going from 1 to k of I, and we claim that this is k times k plus 1 over 2. We can assume this is true, okay? This is the induction hypothesis, or the general assumption. And what we're trying to prove is that Pk plus 1 is true. Okay? In other words, so we're given this, and we're being asked to prove this statement where I replace all the n's with k plus 1s. Okay, so that's the left-hand side, I running from 1 to k plus 1. All right, and on the right-hand side, wherever I have a k, I replace with k plus 1. And so this would be k plus 1 plus 1, so k plus 2 divided by 2. Okay, so that's what I'm trying to prove. And so let's do the mechanics of this. I'm sure you've seen this or something very similar before. So looking at the left-hand side here, we see that this summation is the original summation in the hypothesis. So sigma I going from 1 to k of I, right, plus the additional k plus 1. Okay. Now, I can replace this sum with the right-hand side here because I'm allowed to assume this equality is true. Okay, so when I do that, I now get k times k plus 1 divided by 2 plus k plus 1. Okay, and now a bit of algebra should take you to the right-hand side here. What you would actually do is multiply and divide this by 2. Right, so now 2 is common, so you get the 2 here. And then here, if you factor away the k plus 1 to get this, you're left with k and the 2, which you add to get this. And so that would be the proof here. Now, again, I kind of want to remind you why all of this works. And so let's talk a little bit about the philosophy of induction. The philosophy, especially as it relates to this problem, goes like this, right? Remember now, we're trying to prove that Pn is true for all values of n greater than or equal to 1. This idea that we have to prove an infinite set of things, which seems really daunting when I look at it first. Okay? So what a proof by induction is doing is it's proving two things. It proves P1, okay, which was the base case, and then it proves that if Pk is true, then Pk plus 1 must be true as well. Okay, so this is an implication in logic, right? So here's how I like to think about this. I like to think of all of these propositions as forming an infinite staircase. Okay, kind of into the clouds type of a staircase. And so the first step here corresponds to P1, the second one corresponds to P2, the third one corresponds to P3. At some point, maybe I have Pk, Pk plus 1, and the idea is this goes on forever, okay? Now, what is happening here is statement 1 here claims that gives us this information that this proposition is true, and so you can think of that as sort of getting onto the first step, okay? So if this is 1 of us here, okay, we are now standing on the first step, okay? What the second part of the induction proof does is, what it says is, if you're on step k, you can definitely climb one more step and go to position k plus 1, okay? And you can do that for any value of k. Any positive integer value of k. So what that means is that if I can get onto the first step, and then having gotten onto this first step, I make use of this to then get on the second step. But now I'm on the second step, so I can make use of this to get onto the third step, okay? It's kind of like saying, if some of you have maybe attempted the Manitou incline in the Manitou Springs area near Colorado Springs, I mean, so there's this like really long staircase up there. And I've done this maybe, 2 or 3 times so far. And it can get pretty tiring. And so this is what I tell myself when I'm doing this, right? If I can just go up one more step, and I'll be okay. Because if you can always say this, that wherever I am, I can certainly go up one more step. So if I'm on step number 75, I can definitely get to step 76. But now I'm on step 76, so I can definitely go one more step. I know I have it in me to go up one more step, so I can get up to step 77. And so if you take that argument to the extreme here, you can essentially climb up an infinite staircase, is what we're saying. Now, you and I know this is not going to work on the Manitou incline, right? And the reason is that there's going to be some step. Well, it actually does work on a Manitou incline. It's not going to work on an infinite staircase, because there will come a point, however fit you are, however much you've trained for this, there will come a point where you reach a step where you cannot go up the next step. Okay, so in fact, where that proof breaks down is in part 2 here. Okay, but again, this is the idea that if I can get onto the first step or the first rung here, and if I'm guaranteed that if I'm on a step I can always go up one more, then essentially that tells you that you can climb up an infinite staircase. Okay, and that's where this comes from. Now, so that was our quick review of induction. I will remind you that induction comes in a few different varieties. There is strong induction, weak induction, and again, I mean, so we don't really have time to review the whole thing, but you should if you feel you're rusty in this area, you should probably review some stuff from discrete math.